let's go ahead and start the recording. All right. So, first thing we want to know is what exactly is an inductor?
Uh, Charges are not able to move freely. They're like stuck in one place.
Could you elaborate a bit more? Why would they be stuck in one place?
Uh, let's see. I honestly, I honestly can't really think of the reason.
So, describe more physically. What does an inductor look like?
I guess a tube,
It's
like
elaborate.
you're elaborate this, elaborate that. Uh,
So you said a tube. So if we want to visualize a tube, um, so I'm gonna literally draw what you're sort of describing here.
well, okay. Charges are not able to move freely as well. The magnet field will go through through the tube, and there will be a current going into a certain direction. But
So there's a
trying-
so there's a magnetic field in the tube, and a current is moving a certain direction.
yeah,
So how does the current actually flow?
uh,
Like just through the tube like this?
no, it should be like well, actually, okay, no, hang on. The I is the current, and the way from the picture, the current is going around the tube,
Exactly.
like yeah, like a clockwise or counterclockwise.
Exactly. Yo, how's it going, Sean? We're talking
Doing
about
pretty good.
We're talking about inductors. And because I just got off of an 8-hour workday and drove an hour from Frederick, I have nothing prepped, so we're just talking through theoretical stuff and talking through the main concepts, and then we're just going to look at discussion, homework problems, anything you guys want.
Sounds good.
So, so yeah, Roger, exactly what you said. The charge, essentially, it's a coil. So the wire is essentially a coil of charge that sort of looks, sort of coils around like this. It's like obviously very horrible drawing, but it's essentially they call it a solenoid, or
Okay. So
is
okay,
that
that's
is
that
that
picture.
is that right? Yeah, it's a cylindrical coil of wires. Yeah, it's essentially this is a
Okay.
better visualization.
Okie dokie.
So you have this coil of wire going around, and as the current goes through, you mentioned something about a magnetic field. Why would there be a magnetic field here?
Uh,
How are magnetic fields created? Think back to Unit 18.
yep, that's what I'm trying to do. I
Which one was
just
current? Was Unit 18?
Hmm?
Which one was Unit 18? I forgot.
That would be like Ampere's law.
Oh. Oh. Right.
Or no,
I
the
just
Biot-Savart law. Ampere's law was Unit 19. Yeah, Unit 18, Unit 19. How?
I literally just cannot remember the name. I know there's supposed to be the magnetic. It's supposed to be B is equal to U naught times I over 2 pi r. I just can't remember
So
the actual name.
yeah. So that's the Biot-Savart law. So what exactly? So essentially, what do you mean here? What this mu naught I over 2 pi r? That's the magnetic field for what?
for a current, correct?
Yes, exactly. And in this case specifically, a long straight current. So for a long straight current, the magnetic field is created. The strength is mu naught I over 2 pi r. And what direction is the magnetic field in? Let's say the current's going up. What does the magnetic field do to this look like?
It's going up on the left. Yeah, left side should be out of the page, and inside should be to the right should be inside the page.
Yeah, so it essentially loops around our wire. And so yeah, right hand rule, you can find the direction of the magnetic field. So essentially, wire carries current straight, magnetic field loops around it. So essentially, magnetic fields are created by moving currents. And yeah, that was sort of what I was looking for. And in this case, we got quite a bit of moving current, right? This drawing is ugly. I'm actually going to go ahead and yoink. Let's see. What's a nice little drawing we can yoink?
Yes, plagiarism.
Yes, exactly. Let's see. Copy image. Let's go ahead and yeet this. What? This is a scam. I thought it was going to be clear.
Yeah,
See?
a lot of sites do that.
Whatever. Wait, you know what I can do? Hold up. Pause with me. Please. Hello?
Are you really going to just make it white?
I can't! This is sad. I can't. It's not letting me. Whatever. So, but yeah, let's zoom out a little bit. So we got a bunch of wires here, right? And it's not a straight wire. So
it's a curly wire, basically.
It's a curly wire, exactly. So what is the magnetic field going to look like for this wire?
It should be going through the center, correct?
Mm-hmm. Yeah. What is it going to look like? Is it just going to go straight through the center? Is it going to curve with... I wanted this to be...
I think straight through.
Wait, hold up.
I think. Hang on. Well, that's...
Let's go! It worked! Okay, wait, can I get these little... Nope, damn it. Why am I doing this? Yes. Oh, yeah. Oh, yeah. Yes. Let's go. This is a win.
I think it's supposed... Like, in general, it will go through?
Yeah,
I
exactly.
don't know. Yeah, okay, then.
Yeah, it's going to go straight through the center. And also, it's going to wrap out of either end. If you were very observant, you would notice actually there's a nice little drawing right over here. And one of the other images, like pretty much every single other image I use apart from the one I actually used, has the drawing of what the magnetic field is going to look like. So essentially, the magnetic field passes through the solenoid and also wraps around, but we don't care about that. It's going to be much weaker on the outside. So we have that magnetic field due to our wire, and you mentioned earlier, how do we find the strength of this magnetic field?
The unit current over 2 pi r.
That would be for a long straight wire. Do you know how we find it for this wire?
Okay, so it would be U naught N I this time.
Exactly, mu naught Ni. So obviously mu.
I keep calling it U naught, and I'm like, it has a name.
Yeah, mu naught Ni. And what is N here?
Number of wires? I don't know what. Yeah, it should be number of wires, because I almost said number of turns. That's...
Well, either way is correct, and more specifically... Sean, were you gonna say something? Were you gonna say something?
No.
Okay. I saw your mic pop, the little green thing popped up. I was like, is he trying to say something? Am I cutting him off?
No, sorry.
Okay. So it's like number of wires or number of turns. A little bit more information. I want a little bit more. What's the difference between big N and little n? So, like, for example, for magnetic moment from Unit 17, we have big N times I times A. But here it's little n.
Uh, I don't know. I only know it's just the number
Choice?
of players.
What was that, Sean?
Stylistic choice?
Unfortunately not. Okay, I'll give you guys one more chance here. You guys remember, you might not, you might have forgotten this completely, but back at the beginning of the semester, we went over thermo, right? And remember the ideal gas law? We have PV equals nRT, little n, or we can write big N kBT. What's the difference between the n's here?
Yeah, I definitely cannot remember the differences. I
Okay.
mean, I do know there's supposed to be a difference, and I believe it's like, one's a constant value and the other one is not, and that's the big N. The big N is the constant value.
What do you mean constant value?
Uh 6.022 times 10 to the 23rd.
Okay, so not quite. So big N is for PV equals NKBT. It's the total amount of molecules. Period. Like
Okay.
if you have 7 billion trillion molecules, big N is that exact number.
Okay then.
Little n was not the number of molecules, but it's the number of moles of molecules. So big N would be little n times 6.02 times 10 to the 23.
Oh, okay then.
And you can sort of draw a parallel here, where big N for magnetism with mu for the torque, magnetic moment. Big N is the number of turns. It's the total number of turns in a wire loop. What do you think little n is?
So I guess that should be big N times little n in that case. Number of turns times n.
No.
Not quite.
Nope. Little n is the number of turns per unit length.
Oh.
So it doesn't matter. So that way we can more accurately quantify the magnetic field regardless of how long the solenoid is.
So basically, I was just not getting the SI unit.
Yeah. Or you were thinking you had the right idea. It's turns, but it's more specifically how many turns per unit length. So in this case, it'd be like 3, 4, 5, about 15 turns. I don't feel like actually calculating them. And let's say it's over like 1 centimeter. That'd be whatever 1,500 turns per meter. So that's what little n is. The turns per unit length. That's the magnetic field inside our solenoid. So what does that magnetic field do? Like it goes, so that magnetic field, which is created by our current. So we have a current that's inside a magnetic field, even though it is the one generating the magnetic field. Because the magnetic field, due to each little turn, will affect all the other turns and vice versa. What happens to a charge moving in a magnetic field?
I believe the potential differs. The potential energy, I meant to say, but
I mean, you could.
I mean that does happen on this case, but I know it's not the actual.
Yeah.
Answer
So
to the
what
question.
happens to a charge? Let's say we have a little proton that's all happy and moving along here, and it's going to enter a magnetic field, let's say into the page. What's going to happen to the proton?
It'll want to move to the positive direction.
For a magnetic field?
Oh, whoops! I'm thinking about that loop thing again.
What do you mean loop thing? What happens to our proton?
Well, it definitely moves. It doesn't just move to the, as we're saying, to the right. It will definitely move in a. It will definitely rotate. I should say, like it just goes to an angle.
It's going to curve.
Curve. That's what I was trying to figure out.
So
I know it's not a straight line, but how do I was gonna say it was like curve?
So Newton's first law: an object in motion will stay in motion, in the same motion, until acted upon by a force. There is a force acting on the charge. Basically, that's what I was getting to. A charge moving in a magnetic field, there's a force acting on it. And the solenoid happens to generate a magnetic field, which then goes back and affects the current itself. The magnetic field, which is created by the current, then starts messing with the current that created it. So we have this solenoid which has a certain inductance. What exactly is inductance? There's a formula here on your formula sheet for inductance.
Oh, I thought you were actually asking what's the actual term inductance means.
Well, I mean, it's like one of those things where it's like nothing in physics really makes sense. So if I ask you, what is gravity? What is inductance? What is magnetism? You're like,
it's gonna be the magnetic. It's gonna be the magnetic flux over the current.
Exactly. This inductance L is equal to the magnetic flux through the it's the magnetic flux through our solenoid over the current, which we know how to calculate the magnetic flux, right?
Well, there's a few ways, yes.
How can we calculate it?
Oh, whoops, that's current. Hang on a second. B times A, or at the very least, the integral of the magnetic field dot dA.
Exactly. Magnetic field dot dA, which we're going to assume that our magnetic field is constant, and then it's just the magnetic field times the cross section of our inductor. So it's just essentially mu naught NIA divided by I, so mu naught NA. But so that would be our inductance. Essentially, our inductance is a way of quantifying the inductor's... You know what? I don't actually... Inductance. Let's see what Google says it is. The property of an electric conductor or circuit that causes an electromotive force to be generated by a change in the current flowing. Yeah, you know what? Straight over my head. I'm sure it's even further over you guys' head. It's essentially a property of the inductor, which we can use in a few equations to be able to calculate stuff that will be on your quiz tomorrow. That's about the best way I can put it. So, an inductor is sort of like a capacitor. Remember with capacitors and RC circuits?
Well, yeah.
Yeah, what happens when we have, let's say we're going to have a battery, and then we're going to have a resistor and a capacitor, and we're going to have a little switch, right? And let's say the switch is going to be open for a long time, and then we close it. What happens with the capacitor?
It's a wire.
It's a wire, and what happens over time?
It gains charge, and then after a very long time, it becomes an open circuit.
Exactly. So essentially, our capacitor charges up, and over time, it goes from being a wire, so all the current's going through it, to then eventually there's no current going through it and all the current will go through the resistor. And so we can sort of quantify how it charges or discharges using this time constant, if we remember from, let me pull up the circuits formula sheet. This time constant, R equivalent over C R equivalent times C equivalent, essentially for the whole circuit. So the capacitor charges up. Remember we had that like e to the negative t over tau. So the current through the capacitor starts very high and then tapers off down to nothing, so it looks something like this. And it's e to the negative t over tau. And the charge on the capacitor, or I'm going to say the voltage through the capacitor, is going to essentially increase and approach an asymptote. So this is V and this is I through the capacitor. That's when it's charging. And then we disconnect it. What does the capacitor act like?
Battery?
Mm-hmm. And what does it do over time?
The
Sorry, one of you at a time. Roger, go first.
losing the charge?
Mm-hmm. And then Sean, you're going to say something?
I said dissipate.
Dissipate. Okay, yeah. You guys both talked at the same time, and Discord ate both of your messages up, and I didn't hear either.
Yeah, I was just like, oh god, what happened there?
Yeah. So essentially, the capacitor dissipates, or it loses charge. And so, what does that look like for the current? The current through the capacitor. Initially, right when we disconnect the battery.
Starts to flow, but then loses that flow.
Exactly. And it's going to approach 0. And then the voltage?
Should be the exact same.
Exact same.
It should be max voltage and all the way down to 0.
Exactly. So a capacitor, let's say, so we'll say charge, discharge, goddamn, charge. So the capacitor, when we can charge it or discharge it, and it's essentially going to look like this, where we have the charge building up and then dissipating. An inductor is sort of similar, where when we let's draw the exact same circuit here. So we'll have a resistor, and we'll have an inductor, and we'll have the switch. The inductor acts somewhat similar to the capacitor, but slightly differently.
Different as in opposite.
Different as an opposite. Elaborate.
Right after it closes, it's an open circuit, and then after a long time, it becomes a wire.
Yeah, pretty much. So when we close our switch, and so we connect the inductor, we connect the battery to the inductor and resistor. At first, like you said, the inductor, essentially, there is going to be no current flowing through it initially, just for that first moment. But what's going to happen to the current?
Increases, basically. It's going from no current, and then it'll start gaining the current to, and then it'll just hit an asymptote, I believe.
Exactly. So the current starts at 0, but quickly increases and asymptotically approaches a max value. What about the voltage through the inductor?
That would be VL, correct?
Yes.
Then that should be at a max charge to 0.
And why is that?
Uh, uh, because I keep forgetting what that is called. DI over DT is going to 0. The magnitude of that becomes 0.
What is DIDT?
That's what I'm trying to remember the proper name of that.
Sean, you want to help me out?
Hmm?
DIDT. Come on, you guys have taken Calc 1, right?
A while ago.
I mean, yes, I know it's a derivative, and I
It's a
know
derivative! It's a derivative. What is a derivative?
Well, a change.
Exactly.
That's what I mean. I don't know what the actual change is, like the name of that change.
Well, it's the change in current. That's what I was looking for.
Okay, so it's
Yeah.
that simple. Okay.
Yeah, you're overcomplicating it. So yeah, it's based on the change in current over time. What's the change in current initially? It's pretty big, right?
Max. Yeah, it's that max, basically.
And then
max.
as it approaches the asymptote, it becomes much flatter and it goes to 0. So that's for the charge. I'm just going to signify that with a C. Now, what happens when we disconnect the battery and the inductor acts? What does the inductor act like?
Does it too act like a battery? I mean, I know the current is at max and then decreases, and the same thing with the. It's the same thing with the. I don't know why I want to keep saying velocity, voltage. In that too.
So you're saying the current starts at a maximum and decreases?
Yes.
Mm-hmm. So therefore, what would the voltage be based on the current graph?
It will also decrease.
Exactly. It starts at a maximum and decreases down to nothing, because as you can see, based on the slope of the current, we start at a maximum and we decrease and it becomes more flat. So yeah, that's pretty much, that's inductors. I guess the other main thing is, how do you quantify the energy stored in an inductor?
UL is equal to 1/2 times LI squared.
Yeah, exactly. It's just
What's funny is I did do some the homework. I don't think we even did that in the homework.
Yeah, honestly, I don't remember ever literally not once in my entire time studying physics did I ever worry about the energy stored in an inductor.
Did I even use torque to find anything? The unit 22 one with the T.
Torque is equal to mu cross B. I wouldn't rule it out. Just because you didn't on your previous quiz doesn't mean you won't on your final quizzes on Friday.
No, I'm talking about on unit 22. The L equivalent over R equivalent.
Oh, so that's not torque. That's tau, and it's similar.
Why? Okay, so why are you using whatever?
So this tau is similar to the tau from capacitors, where essentially it's a time constant, where it relates to how quickly the charge and voltage increase or decrease.
Okay, so that's probably I think that was on one of the homework things.
Yeah. So for example, for this voltage here as it charges, I'm going to label this discharge. So for the voltage as it charges, what does this graph look like?
Oh God. Is it the 1 over X like we always? Wait a minute.
It's not 1 over X. It's an exponential.
Oh dang nabbit! It's that 1 minus. Okay, that would explain why why it was using 1 minus e to the negative x then.
Yeah. So in this case, it's not 1 minus e. It'd just be e to the negative And in this case, it's t over tau, the time constant. And same thing for these two. It's e to the negative t over tau. And for this one, what is it?
Would that be the 1 minus e to the negative tau?
Yep, exactly.
Okay.
This one would be 1 minus e to the negative t over tau.
I think that would explain why the heck it was at what, because there was one question I was like, okay, how the actual heck do I find this? And then, I actually did use Chegg to figure that one out, and I was like, why are we using that? Nothing in my formula sheet says that.
Do you want to pull up
Now
that
I
question?
see why.
Do you want to pull up that question and take a look at it?
Sure, if I can remember which one it wasn't. Okay, I think it would be that. So, give me a minute. I need to get this too because
Yep.
if it will pop up.
Take your time.
Yep.
And Sean, do you have any questions about this?
No, it seems good for now.
Yeah. It's honestly, especially with how you guys don't have to worry about actually deriving inductance or deriving the voltage. Basically, nothing you guys do in this class actually worries too much about deriving things, and that greatly simplifies things, and it's honestly not much to worry about. You just have to know and understand the equations and know how to use them on examples. The best way to do that is practice.
Almost put in the wrong one. There's that part, and then
Okay.
that, and then the actual question. I might as well have that so that way you get some of the numbers.
Okay. Yeah. So let me just do this. Copy, paste. And I don't even need to have that open. Let's go ahead and just do this. Okay, cool. So the circuit is constructed with the 4 resistors, 1 inductor, and battery, and this is blah 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 numbers. Okay, so we have a circuit with a bunch of resistors, and we have the inductor. So after the switch has been closed for a very long time, it is then opened. So what is going to happen to the current through the inductor? Is it going to increase or decrease? And is it going to start at a maximum or a minimum?
After the switch has been closed for a very long time, it is then open. At that point, when it's open, actually the current should stay the same right at that point.
And then what will happen to it over time?
It will decrease. Over time, it will definitely decrease, yes.
Exactly.
But at the moment of we opening it, it will be staying the same.
Exactly. It's going to decrease, and it's going to be an e to the minus t over tau, right? Because it's an exponential decrease.
Okay.
The current, so it asks, it's closed for a very long time, then opened, and it's asking what is I3, the current through the resistor R3, at a time t equals 6 milliseconds after the switch was opened. So is I3 going to be different from IL in this case?
Excuse me. Yes.
Why would it be? Would it be different?
Oh, for the current? Oh,
Yes.
no, it wouldn't. Sorry,
No,
yeah, no.
no. I3 and IL are going to be the same thing. So we know I3 is going to be starting at a maximum and it's going to decrease as a function of time with E is equal to negative T over tau. So, how do we actually find tau, and how do we find the initial current, the constant I naught out front? Those are the two things we need, right? Because we know how long it's been. We're looking for the current 6 milliseconds after the switch is opened.
Let's see. Well, tau is equal to L equivalent over R equivalent.
Mm-hmm.
Let's see. I believe we only need to worry about one L.
Mm-hmm. So tau
And
is equal to L over... And what is our R equivalent, our total net resistance?
I'm guessing we only need, because since I got it, I'm guessing we only need the two resistance of R2 and R3. I guess, and probably because of like Kirchhoff's rule.
Why wouldn't we need to worry about R1 and R4?
Um. Oh, it's specifically asking for the current I3. R1 and R4 are not in that type of current, not even within IL.
And why aren't they?
Uh,
Why
because
wouldn't
of the
why wouldn't there be a current going this way?
Because the switch is open?
Exactly. Switch is open. Mwah. Amazing.
okay, yeah, that makes sense. Yeah.
Switch is open, so nothing past not that point. Nothing past this line matters.
That's I even said Kirchhoff's rule, so I should have just realized. Yeah, draw the loop.
You probably had the right idea in your head. So yeah, we don't need to worry about R1 and R4, so it's just the net resistance of R2 and R3. How do we get that?
They're in series, so R2 plus R3.
Exactly. R2 plus R3. So now we want to find the initial current through the inductor just as the battery is disconnected. We want to find I naught. How do we get that?
Wouldn't that just equal to I3?
Would it be?
Let's see.
Well, sorry, I should say yes, I3 and IL are going to be the same thing right after it's disconnected. But we want to find the actual value of it, and we don't know what I3 is. How could we find the value of IL?
Oh, okay. Well, in one of the questions they asked you about how to find IL already, so
Mm-hmm.
IL to find that. Uh, oh boy, you have to even use I4 as well in that case, because
How is the current through the inductor? Sorry, wording. Come on, Dylan, you can do this. You only had to retake English once. You can speak a full sentence. How is the current affected? How is the current through the inductor affected by the switch opening? Like the moment before the switch is open versus the moment after the switch is open. How is it changed?
the current flowing from the battery on before was from the battery right back to the battery, but as soon as you open it, it now doesn't even doesn't even go towards the battery. It's just the loop between R from to R3 all the way to L and back to R3.
So does the current through the inductor right when we disconnect the battery, does it increase or decrease, or does it just stay the same?
You said disconnect the battery, right?
Yes, we're opening the switch.
Right after we open it, the current should stay the same, and then after like literally 0.1 of a second, it will start to decrease.
Exactly. And not 0.1, 0.0000000 a million zero.
I didn't want to just go with all that.
But yeah, you're right. It's going to be the exact same as before the switch is open. So essentially, we need to calculate what IL would be if the switch is closed, and it's been closed for a long time. How do we do that? Well, first of all, what does the inductor act like when the switch has been closed for a very long time?
Wire, correct?
Exactly.
Right.
Acts like it acts like a regular wire. So, essentially, we just ignore it. It's just a regular wire. So essentially, all we need to do is find the current through R2. We know how to do that, right?
Yeah, that would be current of R2. So that's parallel to R3. You know what? If we just say that that's to the wire, and then it just be the series of R1 and R2. I mean R4.
Mm-hmm. So what do we need to do to find I2?
To find I2, you need to equal it to the voltage over R2. The voltage of 2 over R2.
Okay, so that's a good start. So let's say, I'm just going to write this down here. So I2 is equal to V2 over R2. Sure.
And and then we need to figure out what the voltage is, because we're given the resistance but not the voltage. And then the voltage of 2 should equal the voltage of 3.
It's equal to V3. Sure. Keep going.
And then V3 will equal the sum of V1 and V4.
Close, not quite. It's related to the sum of V1 and V4.
Let's see.
What's Kirchhoff's loop law?
That's what exactly I'm trying to remember of that. Let's see. Trying to find a parallel one. That's parallel.
What's the loop law?
Oh, so it's supposed to be is it minus? Then hang on.
Please, sir, I have forgotten loop law. I need you to help me.
Yeah, I think so. I think I forgot some stuff on that.
Calling in Sean for backup.
There's a reason why I haven't said much in a bit.
do you remember Kirchhoff's loop law?
I remember of it.
Just not specifically.
It involves voltages. Come on, you guys can do it.
I mean, I know it's supposed to be from at least formula wise, it would be from V, so VB minus I1 R1 minus it should be minus I3 R3 minus I4 R4, and then the current from I1 and R4 should be the same.
Exactly. So essentially, voltage around any loop is 0. So So this voltage V3 or V2, either way, because we can draw this loop or this loop, is equal to V of the battery minus V1 minus V4, which, as you said, each of these voltages is equal to IR. So let's go ahead and write this down, and I'm going to use the numbers because anytime there's a number here, I'm going to use it because it makes things simpler. So let's use V2 here. So we have V, which is what's the voltage of the battery? 12 volts.
Yes.
Also, I'm going to move V2 over to this side, so it's going to be V minus V1 minus V2 minus V4 is equal to 0.
Makes sense.
So 12 volts minus V1, which is I1 R1. R1 is 50 minus 50 I1 minus I2 R2. So minus 50 I2, which is what we want to solve for, minus R4 I4. I4 is equal to I1, like you said. R4 is 148 ohms. Screw these numbers, they're dumb.
Yeah.
So minus 148 I1 is equal to 0. And then we could combine these two in, so it's going to be 50 plus 148 is 198, right?
Yeah.
So minus 198 I1 minus 50 I2 is equal to 0. We have one equation. Now, we need but we have two unknowns. We need another equation.
Oh God. Okay, you're going to do that matrix thing.
Well,
I understand.
Is there any other option for us here? No.
Well, okay, no, but I will have to say, the previous question beforehand, because this is question number 4, we did figure out what I1 is, so I will let you know on that case.
How did you get I1?
Well, it says if the switch is oh, hang on a second. I need to make sure I'm reading all these questions correctly. Okay, it was number 2 in this case. What was the magnitude of I4 after a long time? And then I just used I just used the voltage over the R equivalent, which in this case was R1 plus R4 plus the parallel of R2, R3.
Exactly. That we can do that. That's a way we have one equation here, we have two unknowns, and we have a way of solving for one of those unknowns. So you said I1, or in this case like I4, I1's the same thing, is equal to V over R equivalent, which you said this is equal to
R1 plus R2 R4.
So 50 plus R4, which is 148,
plus R2 times R3 over R2 plus R3.
So 50, 108. $50, skinny 0, over 50 plus 108.
Yep.
So then, yeah, we just 12 divided by that gives us I1. So let's use a calculator here. So 50 plus 148 plus 50 times 108 over 158. We get a total resistance of about 232 ohms, 12 volts divided by that. We get I1 is equal to about 52 milliamps. So then...
Yep, that's what I got for that one.
So then I2 would be 12 minus 198 times this over 50. Right, because we just move this over to the right and divide by 50.
Yeah.
And we get I2, or the initial current through the inductor is about 35 milliamps, 0.035 amps. So I naught, or I'll call it IL. IL is equal to 0.035 amps. Now we know what we need to do to find I3 6 milliseconds after the switch is opened. What do?
Uh,
We've come full circle back to the original question by essentially solving each question sequentially that you hadn't given me.
basically.
It's almost like there's a reason the questions are in the order they're in. Because he doesn't like to overwhelm you with a question where it's like, it asks you one thing, and to get that one thing, you have to go through like 5 different steps. He just asks you 5 different questions and sort of guides you along the path.
Okay, so now we're trying to figure out the current DI naught. So in this case, we will.
Well, we just found I naught.
Oh, okay.
Right?
Then. Oh, right. We're supposed to try to find the current through R3. My bad.
6 milliseconds after we open the switch.
So that the I would equal IL times. Oh, okay. So it's literally my face on that graph. Then it's literally I naught. The I3 will equal I naught e to the negative t over tau.
Yep.
I guess.
Exactly.
Yeah, tau.
So let's get I naught times e to the negative, and then we have 6 milliseconds, SI units, 0.006 seconds, t over tau. So I'm going to then multiply this by R2 plus R3, and then just divide by the inductance. TR over L, R2 plus R3 is 158 ohms, divided by the inductance, which is 365 millihenries, which moved over 3 decimals to get it into henries, which is the SI unit. And we get a current through I3. So the current I3 after 6 milliseconds is going to be 2.63 milliamps, 0.00263 amps. Is that similar to what you get? Is that what you got?
Yeah, that is what I got, but in a negative.
Ah, yes, that because we only found the magnitude. And so because you have now spoiled the fact that it is negative, we know it's going up. But how would we be able to determine that?
That's the one thing I'm still trying to figure out too. Let's see. The positive direction for the current indicates to the figure. Oh, so since we're using IL and it's going against I3, IL would be in the negative direction of I3, so that's why we had to do negative.
Mm-hmm. But what if we guessed wrong and IL was originally going up? It's not, obviously. Why do we know it's not?
Because how the current was flowing when it was closed?
Exactly. The battery, when it's closed, current flows up here this way. And then we know it is going to go ahead and split into these 2 paths, because there's no battery on either of these paths to mess with the direction. It's all going to flow clockwise around both loops of the circuit. So then, when the switch is opened, the inductor's current isn't just going to pull a frickin' 360 like, whoop-de-doo, wait, let's go the other way. No, that ain't how it works. This is one of the few times where you can actually use some logic and reasoning and be like, nature wouldn't actually do that, would it? Nah,
It will find a way.
Physics finds a way to mess with you, but sometimes you draw the line and you're like, no, it definitely won't do this. But yeah, that's basically how you do it. You find the initial current, which you know is as if the inductor isn't there, and then that current is going to continue when the battery is disconnected, and it's going to slowly dissipate, and the current is going to continue to go in the same direction as it was before. So that means that I3 would have to be going upward. Y'all got any questions about this?
Nope.
Hold for applause. Woo! Let's go! That was our last regular session of the semester. That's crazy, right? That was a quick 6 weeks, 5.5 weeks.
Yeah.
I mean, technically it's been 5 weeks since the first session. Feels like it was just yesterday. And Roger, you didn't miss a single damn one, did you?
Hey, it helps to understand the concepts.
You were here every day, and I applaud you.
Because basically the quizzes were a lot about the concepts. Well, at least the first 3 quizzes weren't as much, but after that, yeah.
Thermo stinks. Thermo's different.
Thermos, I was getting good grades on the quizzes. Everything else, oh boy.
It's the redheaded stepchild. It's the weirdo in the family. But yeah, that's it. So I don't know what my schedule's going to be like for Thursday. For the next 3 days for my job, I am going to be working remotely and just doing a bunch of BS online training. So I don't know specifically what my schedule is going to be like for Thursday. It's a safe bet to assume that I won't be able to host a session at the regular time at 12, though. So
okay.
It'd be a safe bet to assume it's probably going to be afternoon to evening-ish, probably slightly earlier than today, because I didn't have an hour commute. I don't have an hour commute to get home on Thursday.
Okay. All right.
So maybe 4, 5-ish, somewhere in that time frame. I'll let you guys know by tomorrow night.
Okay.
The last session, normally I would like to host a longer session, but I'm not really going to be able to because I'd like to have a life and like actually be able to do something on Thursday. So it's probably going to be normal hour 5, hour 10, hour 15. We always end up going over. But I'm gonna try to put some time aside to prep a few practice problems. Probably just like one thing for electricity, one thing for magnetism, one thing for circuits, and that should take up most of the time.
Yeah. Is the final going to be like focusing more on like the second half of the semester rather than the first half or something like that?
So, he put out the information. He is an announcement on Sunday.
Oh, really?
In announcements here on Discord. So there's 3 quizzes you'll take on Friday. First one's at the regular time. It's accessible from 12:50 to 1 o'clock. And then you have like a 10-minute break. And then your second quiz is 1:40 to 1:50. You're able to access it. And then you have another 10-minute break. And your third quiz is accessible from 2:30 to 2:40. First quiz is on electricity. Second quiz is on circuits. Third quiz is on magnetism.
Okay, yeah, I see it now.
No thermo. So everything after the first week is fair game. Everything you did the last 4 weeks is fair game. And I'd recommend main things to study. If I had to tell you one thing to study for each quiz, first quiz, Gauss's law. Second quiz, just practice breaking down circuits step by step, resistors and parallel and in series and yada yada yada.
Well, technically, this is a nice little practice, but
Yeah,
it's
I mean, like this problem. This problem was cool. Do problems like
yeah.
this. And then the third quiz, magnetism, Ampere's law. You know, or may it's sort of it's going to be probably a toss up between understanding Ampere's law and being comfortable with Faraday's law.
My question is, how many questions are there going to be for 40 minutes?
But each of these is going to be similar to your regular quizzes.
All right, so uh, if
Wait,
each
so
of
we get like about 40 minutes for like about like what 6 questions ish?
probably
Yeah, it's gonna. So I don't actually see your quizzes, so I don't know what they're normally like.
they're
Um,
normally six. They're normally 6 questions, adding up to 12.1
yeah,
points. So basically, it's like or like 6 to 7. Like 6 questions actually would be worth 2 points, and one other question saying, I'm not freaking cheating," and then point one.
yeah. So it's gonna be. It's literally gonna be exactly like your regular quizzes, time wise. It's gonna be like you have 30 minutes to do it, and bada
Oh,
boom,
it's
bada
Well,
bing.
it says 40 minutes. So
Is it 40 minutes?
yeah, it's 40 minutes.
Yeah.
Okay. I'm thinking you might have at least a few minutes in between each. Like I think maybe it's 40 minutes. I guess I don't know. I
And it is saying 3 parts, 40 minutes each.
okay. Does it specifically say that in? Does he specifically say 40 minutes, or are you just going based off the time?
Your final exam will be
Ah, yes, I
on
see it. I
Friday
found it now.
starting. Okay.
I found it now.
I'm
40 minutes
reading.
each.
I'm literally reading the part above the
I
times.
was reading it. I was trying to find where it is. It said 60 40 minutes. Yeah. Um, maybe each one will be just slightly longer. Maybe 7 or 8 questions.
That makes sense. That now makes sense. Yeah, because sometimes depending on how things go, each question could take like a good. Uh, it's like 6 questions, generally 5 minutes.
Yeah.
So like each question 5 minutes each.
Yeah.
So
So
it'd be something like that.
it'll be two questions are probably going to take you about 10 minutes each, and then the rest are going to be quick, like 2 to 3 minute questions.
Yeah.
That's my guess. You know,
'Cause
concept
generally,
questions, two big questions.
yeah, because generally, like I said, it's mostly concepts rather than working out the math. And then sometimes it was, unlike last quiz, was literally nothing but concept, basically.
Yeah. All
I
right.
think there was only one working question, and that was a.
All right. Well, thanks guys for coming. I'm going to cut us off here because I need to go prep for my 121 session that I'm hosting in 15 minutes. They're going to be lucky.
That one.
They're going to be lucky. They're actually going to have a problem sheet prepped for them because I'm gonna have 15 minutes in between. No, honestly, I almost prefer these sessions because it means I don't have to put as much time into it, and I feel like we almost get more out of these ones where we're going over specific problems that you guys have had trouble with.
Yeah, that was. Yeah, this question was just the one of like, where the heck is this coming from? Now I understand where it's coming from.
Yeah, exactly. Mwah. Magical. All right, thanks guys for coming, and probably 5-ish Thursday, maybe. I don't know. To be
Okay,
determined.
thank you.
See ya.
Sounds good. See ya.